Okay. Let's see here. This is a quick video on Chapter 7, Periodic Properties. So, just based on the title, what we're talking about is the periodic table. This bad boy that we love and something like that. Well, that's a terrible periodic table. But this and what physical and chemical properties that are traditional in the periodic table. So that's what we're looking for, physical and chemical properties. First off, let's talk a little bit about some vocabulary that we need to know. Before we talk about ions, what is an ion? An ion is an atom with its gained or lost an electron. That's good. A cation, well, this is positive, meaning it lost a negative electron, therefore positive ion, as in cation. We have the anion. This is the negative. It gained a negative electron, therefore it's more negative ion. Two very, very important concepts, can't do it. So the first thing we want to talk about is the effective nuclear charge. We refer to this as Z effective. So what is effective nuclear charge? This is more or less the power of the strong forces in the nucleus. So it's more or less the power of the nucleus. Now this is really, really important. So we have two positive atoms, positive protons, right? And they're stuck very, very close together in the nucleus. Now to get two positive protons very, very close together, you have to have strong forces around it to keep them together. That's countered by the negative electron. This attraction here is also occurring. So we have the electrostatic attraction of the positive protons and the negative electrons, as well as the strong forces keeping the positive protons together. So we have more or less a balance between the force in the nucleus and the valence shell electrons. So remember, if we think back to we have a nucleus that's positive and we have different electrons, different levels. This distance is shorter than this distance. This distance is longer, so therefore, given to our force of the electron, K, Q1, Q2 divided by D squared. As this distance gets bigger, the force also gets bigger. So more distance away from the nucleus, the stronger force that it needs to keep the electron there. So that's occurring on one side. And on the other side, we have the positive and positive attraction, or strong forces keeping it together. This strong force, we won't talk too much about it, but it's very, very important for the stability of the nucleus. More or less, where you need to know, the effective nuclear charge is power of the nucleus, balanced with the power of the valence shell electrons. So this is important. Balance. So that's what we're going to be talking about today. We're going to talk about how we have power in the nucleus, we have power on the valence shells. How does that balance? How does that teeter-totter work between we have the valence shell electrons on one side and we have the nucleus on another side? Which one's going to be stronger? Which one's going to be weaker? How is this going to move up and down? And how is this going to move up and down accordingly? This is the concept of the periodic properties associated with electrons. I know it's a lot. So first off, we have the balance of these forces. Secondly, how does that affect the anions and cations? How does that affect that? Okay, great. So let's talk about pull up. So if we have a periodic table, now in this direction, this is the direction of the nuclear charge. Here is where it's lowest, and here is where it's highest. This is showing us that an element like fluorine is going to have a very high nuclear charge, which means the nucleus has more power. An element down here, like cesium, has very low nuclear charge. It has less power. And power is going to be referring to the balance between the valence shell electrons and the strong forces in the nucleus. This one is winning over here in fluorine. Cesium down here, not so much. Now, this is really easy to tell the difference between two elements that are opposite sides. Once you get in the middle, between like this one and this one, it gets a little bit more complicated. Like this one, well, it has like 76 electrons versus 45. It's on a different energy level. That makes it complicated. What I'm going to really test you on in class is going to be, look at these 4 electrons. Which one has the highest effective nuclear charge? You would say sulfur. Why? Well, there's our arrow, sulfur. Which one has the least? Well, there we go. So this is the type of questions I'm going to ask. Okay, let's go back. So, another one we want to talk about, electronegativity. This is pulling I refer to this as inward. We're going to pull electrons inward. So electronegativity is how much power, again, does it take to pull electrons in? And remember, pulling electrons. And so if you have an element, fluorine, and then you have an electron out here, can it reach a hand out here and grab that electron? Can it do that? If maybe this electron is too far away, maybe it's close enough, how can it do that? Compared to something like, I don't know, sodium. Can it reach its hand out there and grab an electron? Which one can actually do that and which one can't? This is the question of electronegativity. How can we pull electrons into the atom? Now, if I go back, over here, we also have this look for electronegativity. This is telling us that an element like in this scenario here, this one would be the most electronegative. It can pull electrons in because that nuclear force is stronger and it can pull in electrons. Stuff over here, francium and cesium, really can't pull electrons in. Sodium really has a hard time of pulling electrons. It has a very low electronegativity compared to something like fluorine over here. So in the last model, this had a longer arm. This can reach out and grab more electrons, when sodium really cannot grab enough. But what it can do But the opposite of pulling is pushing. So I want to group 2 things together, ionization energy and electron affinity. Now they're very similar, and for our purposes in this class, we're going to kind of talk about them in the same breath. But ionization energy and electron affinity, this is pushing electrons away. So an element like fluorine, with, you know, if its 2p5 orbital has one open space, it really wants to keep. It does not push electrons away. It's so close to being stable, so close to that octet rule, it's not going to push electrons away. But something like sodium only has a 3s1, it's fine pushing it. It just will push electrons away. The moment it pushes this one electron, it pushes that electron away, it can actually be stable at that point. And so we have this effect of the energy between the nuclear force and the valence shell electrons. And if we push them away, that's really, really good. We pull them in, that's electronegativity. So ionization energy and electron affinity this is going to go the opposite direction. So we have ionization. Ionization and electron affinity. So what we can say is something like over here, fluorine is going to keep its electrons. Bromine will keep its electrons. It really can't push the energy, push the electrons away. It's almost already full. It's really, really difficult. But something like lithium, sodium, even something like radium down here, this will push electrons away. This is an increase in ionization energy. It's easier to push electron away. It's easier to be stable. Fluorine cannot lose any more electrons. It is so close to being stable with 8 valence electrons. So we have this balance, electronegativity of pulling electrons in, ionization energy pushing electrons out. So this is very, very important. This balance, this seesaw effect, is based because of this strong nuclear force. Well, this has one more aspect to it, and that is the atomic radius. Now, as usual, what is a radius? If I have a circle, a radius is distance from the center to the outside, and it's the same across the whole circle. So imagine this is an atom. The radius, literally, the atomic radius literally is the radius of an atom. Now, more specifically, you have a hard time measuring that distance. So if we put two atoms together, we measure the distance between each nucleus, the distance between the nuclei. Distance between the nuclei, well, that gives us a diameter. 1/2 of that is equal to the atomic radius. Blah, blah, blah. Doesn't really matter. We know that the atomic radius is the radius of an atom. So if you have a positive center and a distance, you have a radius. If you have an increased electronegativity, you're going to pull in. Therefore, the atomic radius goes down. But if you have a higher ionization energy, well, that means you're pushing electrons away. That means the radius gets bigger. So with the radius getting bigger, we're pushing more electrons away. This allows us to gain more space in the radius. So if I go back, to the right, if we go back here, our atomic radius goes opposite of electronegativity as well. This means that things like fluorine have a really small atomic radius, and things like cesium down here have a very large atomic radius. So here's small, here's large. And those are the 4 periodic properties you need to know. If you have questions, come see me in class. Excellent.